This video is about rotational equilibrium. So we've looked at equilibrium of forces, and the condition for equilibrium of forces was that the net force equals 0. And that is a vector quantity. And so that amounted to having the up forces equal down forces, and the forces to the right equal forces to the left. And that was when we made our table, and so this is the y component and this is the x component, and we made the table and we made sure they all added to 0. Alternately, we could simply balance the up and the down forces and the right and the left. Now that's called translational equilibrium. And that means that the object won't, as a whole, move left, right, up, down. But now when we're worried about segments of your body that are able to rotate, we have to worry about rotational equilibrium. And the condition for rotational equilibrium is that the net torque is 0. Okay, and what this means is that clockwise torques must equal counterclockwise torques. Or if you were counting counterclockwise torques as positive and clockwise torques as negative, it would be all the counterclockwise minus the clockwise torques would equal 0. But I much prefer to balance them, and then you don't have to worry about negatives. Okay, so what does this mean? So let's consider the classic example is the bicep curl. Now we're not actually curling our bicep. We're simply going to hold our arm in a stationary position. And we're going to hold our arm in a stationary position where our forearm is horizontal. Okay, so let's look at the forces that are on our forearm when we're holding it horizontally. And let's put a dumbbell in our hand here. Okay, so somehow we're holding this dumbbell. So we have the force of the dumbbell. And then we have the force of our forearm, the force of gravity of our forearm. So I'm just going to call this F arm. Now, if those were the only two forces acting on our forearm would rotate. And the thing that's counteracting that is the force in our bicep up. I'm going to call this force muscle, or just FM for force muscle. And we're going to see that actually those aren't the only forces, but there's also a force at the joint. So this is our elbow joint. Okay, so let's look at how we're going to analyze this to write the equations for equilibrium, both rotational and translational. So now we don't necessarily know which way the force from the joint is before we start, but there definitely is a force at the joint. But we're going to look at torques first. So let's look at torques. We've done this in the last unit, but now it's always going to be that the net torque is 0. So you won't be calculating net torque. You'll just be using the fact that the net torque is 0. Okay, so it means that clockwise, this is how I write it, clockwise equals counterclockwise. Okay, remember the definition of torque. Torque is equal to force times lever arm, where lever arm is the perpendicular distance from axis of rotation to the line of action of the force. Okay, it's those perpendicular distances. Now here's where this is a bit problematic. The textbook that I had you use, chapter 3 and chapter 4, to do the reading assignments, they use D for lever arm, but in physics and in the other books I've used and in all the subsequent problem assignments, I'm using L. So this is a little bit of a pain, but I'm going to use L for lever arm, because all my previous solutions use L for lever arm. And unfortunately, D is the distance along your body segment. Now that's opposite to what we just did in the last chapter, and I'm sorry about that, but all my assignments and solutions are already made up, and this is what I've used. So D is the distance along your body segment. Okay, and remember, they're related by a triangle, or sometimes they're equal to each other. It depends how the forces are acting. Like in this case above, the distance along your body does equal the lever arm because your arm is horizontal. Okay, so let's do the torques. So I'm going to draw a horizontal line up here, and maybe I'll draw that again down here. So here's our forearm. We'll put the joint axis of rotation, the left end. We've got the force of gravity of the dumbbell, and then we've got the force of gravity of your arm, and then we've got the bicep muscle. Okay, and in this case, the lever arms and the distances along your body are equal because these are already perpendicular to your body here. So this would be D, always from the axis to the force. That'd be D for the muscle. That would be D for your arm. And this would be D for the dumbbell. We'll just say weight. Okay. Now it turns out that D is equal to L in this case because we don't have a triangle. And D arm equals L arm, and D weight equals L weight. Okay, so you need your diagram first. There's your diagram. You've got your axis of rotation, you've got your lines of action, you've got your lever arms. Next, you need to go and you'd have to decide whether the force is trying to make your arm rotate clockwise or counterclockwise. It's not succeeding because your arm is stationary, but it's going to, even if it's trying, that's the definition of clockwise and counterclockwise. This is trying to make your arm rotate clockwise. So that's going to create a clockwise torque. This is also trying to make your arm rotate clockwise. So that's a clockwise torque. Your muscle force is what is counteracting this, and that would be the counterclockwise torque. Okay, so clockwise equals counterclockwise. So lever arm times force. Force times lever arm, that's the torque from your forearm, plus force times lever arm. That's the torque from your dumbbell, must equal force of your bicep muscle times lever arm of your bicep muscle. And that is the equation for equilibrium. Okay, so that's the equilibrium, rotational equilibrium. Rotational equilibrium. Okay, so let's say that we're told all of these numbers except this. Let's say this is the unknown. And let's say we're given that the weight of your arm is 20 newtons, distance to your forearm is about, I don't know, say 15 centimeters, 0.15 meters. Let's say you're holding a 2 kilograms, so 2 times about, well, let's say it's heavier than that. Let's say it's a 40 Newton force you're holding. And the distance out to the end of your hand is about 35 centimeters. So we'll say that's 0.35. Now, this little lever arm for your bicep muscle, that's the distance between your elbow. Let's go back up to here. It has to be, look, it's within your body. It's this little teeny weeny distance here. It's very small. Your bicep muscle is attached to this bone in your forearm at a very small distance from your elbow joint. It's only maybe about, I don't know, say 3 centimeters. So this is really close, tiny little lever arm. So let's say we're told that this is only 3 centimeters. That's 0.03 meters. Okay, so let's now calculate this force in your bicep muscle. It would be 20 times 0.15 plus 40 times 0.35 divided by 0.03. And this would come out newtons. Let me quickly punch that in my calculator. That comes out to 567 newtons. Much, much bigger than either the weight of your forearm or the weight you're holding. So it's a huge force. Okay, so that's a huge force in your bicep muscle. Now, the next question is, if we look at that, this force of the muscle up, and the two forces down, they certainly do not balance. Up equals down. So now we look at equilibrium of forces. And this is used to find the force in the joint. Okay, so let's look at this forearm again. Got this huge force, 567 newtons from your bicep muscle. You've got the weight of your forearm and the weight that you're holding. Clearly, the up force is way bigger than the sum of the down forces. Your whole forearm would go flying straight vertically up toward the ceiling if this were the situation. So something, obviously, the force at the joint must be down like this. And that's due to your upper arm bone pushing down on your elbow. So it's because of your upper arm that your whole forearm segment doesn't fly up to the ceiling. And what must that joint force be? So we use up equals down. So we have the 567 must equal the force in the joint plus 20 plus 40. And so it's a fairly big force in your joint here. 567 minus 60 is 507 newtons. Okay, and so that would be the force on the joint from your upper arm pushing on your elbow. Now that, we didn't put that in the torque equation because there's no lever arm. This is no torque. There's no torque from this force because it's right on top of the axis of rotation. And so your upper arm does not exert a torque on your lower arm. It's your bicep muscle that exerts the torque. So this is no torque on lower arm. Okay, so that's how the equilibrium questions are going to work. Now let's just quickly do, what if I don't have my hand horizontal? And what if I just move my arm down a little bit like this? Now, we'll still have the bicep muscle go straight up. Sometimes, I mean, it doesn't really go straight up. It sort of goes at an angle, but we'll just keep it straight up for now. So there's your biceps. The only difference here, let's keep this 40 newtons, and let's keep your arm 20 newtons. The distances along your body, D, are the same. So D stays the same, and that's the distance. D for your muscle is still 3 centimeters, and D for your arm is still 15, and D for the weight is still 35. But the thing that's changed now is the lever arms have changed, because remember, the lever arms are the perpendicular distances. So we need to get the distances along this horizontal line here, where this is theta. And this is now where you're going to have triangles to get the lever arms. So in every case, looks like this. The lines of action slice this like this. D is the hypotenuse. L is the perpendicular distance. And so, and all the triangles are the same. So if you go this one, this would be L for the arm, and this would be D for the arm. And then out to here is L for the weight. And then along the hypotenuse is D for the weight. And they're all the same triangle. And the deal is that this L is close to the angle. So L is cos. So L muscle is D cos theta. L arm is D cos theta. And L weight is D cos theta. So it's always cos theta. And now you just recalculate all those, so they would all be different depending on theta. And then you proceed exactly as you did before. The equilibrium equation for torque is the same. The muscle times the lever arm. For the force of the bicep muscle, is, it doesn't matter whether you go lever arm times force or force times lever arm. It's kind of more catchy off your tongue. Lever arm times force, lever arm times force, lever arm times force. That's torque. And now, even though your arm is at an angle like that, up and down is still the same. The joint force is still straight down, and the bicep forces and the weight and the arm are still straight down, even though your arm's at an angle. It doesn't matter if your arm's at an angle like this. So the up equals down is the same. Okay, so that'll do it. I'll then do a video about your assignment and go through some of the diagrams to get the lever arms in the next video.